Hello everyone, welcome to another video of quantum field theory. In today's video, we'll be continuing from our last video and solving for the Unruh temperature. So here we have two ponies. We have Twilight and Rainbow Dash. And we can see that Rainbow Dash is accelerating. She's moving forwards. And Twilight Sparkle, she's an inertial observer, so she is stationary. And Twilight Sparkle is going to see a vacuum. She sees no particles present. So she says that we are in a vacuum. And then Rainbow Dash, she's accelerating. She's going to see particles in what Twilight Sparkle calls a vacuum. And she will see particles because Rainbow Dash sees a horizon behind her. And this horizon is going to release horizon radiation. And that radiation is the particles that Rainbow Dash sees. Now, Twilight Sparkle, she has a flashlight over here. Twilight Sparkle might try to communicate to Rainbow Dash. Maybe Dash is going too fast. So Twilight will send a message with a flashlight to catch up to Rainbow Dash. But because Rainbow Dash is accelerating, some photons that Twilight releases might not catch up to Rainbow Dash. And that, of course, is going to form that horizon that we see. But if Rainbow Dash just slows down, the light beams will catch up to her. And then she will finally see the same vacuum that Twilight sees. So we are going to actually calculate for the temperature, the Unruh temperature, that Dash is going to see due to her acceleration. So we are going to do that now. So Twilight is going to use this mode expansion, and A of k acting on the vacuum state is going to give us 0. Analogously, Rainbow Dash is going to use B of p acting on her own vacuum state is going to give 0. That defines what she calls her vacuum state. So here it's going to be 0b, here is going to be 0a. And our goal is to calculate B of p and B conjugate in terms of Twilight's basis. So A of k and A conjugate. And the way to do this is by using the Bogoliubov transformations, which is this over here. And recall that the number operator in Dash's perspective, well, the exponential value of the number operator in Twilight's vacuum is going to be equal to the integral over dp, I think, and then beta kp squared. Or actually, it's the integral over p and another integral over k, beta kp squared. So essentially, we want to write out Dash's annihilation operator in terms of the creation and annihilation operators that Twilight uses. And this beta over here, once we get that, we can just square it, and that will tell us the number of particles that Dash will see in Twilight's vacuum. So that's our main goal for today's video. So how do we do that? Well, all we have to do is, it's kind of simple, at least the first steps. We want to take Twilight's quantum field. We should note first that this integral runs from minus infinity to infinity. So we have an infinite range of momenta. So what we want to do here is we want to first note that we are dealing with a massless scalar field, because the quantum field in the Rindler space, right, we found that it's only analogous to Minkowski's space for when the mass is equal to 0. So we want to deal with a massless field, and we know that for massless fields, the energy is equal to the momenta, or better said, the energy equals the absolute value of the momenta. This means that we can rewrite this integral as the integral from negative infinity to infinity dk over 2 pi square root of 2 absolute value of k and then a of k e to the minus I absolute value of k t e to the I k x plus a conjugate k e to the I absolute value of k t. You guys get the gist of it. So now for absolute value functions, we know that we want to break it down to two parts, one where it's negative and one where it's positive. So this is going to equal 0 to, or negative infinity to 0, dk over 2 pi square root of 2k times a of k, and here's where it gets tricky. It should be a plus I k t. We want to change the sign because k is going to be negative in this range, right? So since it's absolute value of k, we should put a negative sign in front of that and now make it be positive. Kind of strange, but it does work out. So we'd have e to the I k x plus a conjugate k e to the minus I k t. Again, we just change the sign, e to the minus I k x. We don't change the sign in front of this over here because the momentum can be negative, but the energy can't. So then it should be this plus the integral from 0 to infinity of dk, which is the same thing as before, a of k e to the minus I k t e to the I k x plus a conjugate k e to the I k t e to the minus I k x. Here we don't change this to be a positive because this is in the positive domain. So this plus this is going to give us this over here. So what we can do now, this part I'm not really so sure on why we can do it. We can say this is equal to the integral from 0 to infinity. So what we're doing here is we are combining these and under one integral, and where the integral is running from only positive values for k. These over here should be negative, by the way. These should be negative. And yeah, that's the modification needed. So we say that we are integrating from 0 to infinity, and to adjust for that, we change this k here to be negative k. But again, is that really valid? I'm not really sure. But let's just go on from this. So now what we can do is we can combine these together, the exponentials. That's going to give us 0 to infinity. So that gives us this over here. Again, it's just the exact same thing as over here. We are just rewriting it in a bit of a different form. And now we can use what are called light cone coordinates. So light cone coordinates, these are defined as x plus equals x plus t and x minus equals x minus t. So these are coordinates to use to make our analysis a bit more simpler. So under light cone coordinates, we'd have v of x plus x minus, then we'd have a of minus k e to the I k. Here this is going to be x plus, this is going to be x plus, here's going to be x minus, and here's going to be also x minus. So if a of minus k e to the I k x plus, we're running out of space here, so let me just move this over here, plus a of a conjugate minus k e to the minus I k x plus a of k e to the I k x minus plus a conjugate k e to the minus I k x minus. So I hope what I've explained so far doesn't seem too confusing. We just introduced new coordinates to make this just like one thing, just to simplify that. That's all we're doing over here. So now we have this, and that's for phi. I'm going to write this out again as phi of tx, just to remind you guys that we are still using the inertial Minkowski coordinates, but we can also write it as x plus and then x minus. So if we were to do this exact same thing for the rainbow dashes coordinates, we would get something very similar. We'd get that phi of epsilon, or n epsilon, would be the integral from 0 to infinity of dp over 2 pi square root of 2p b of minus p, and then plus b of p e to the I b. This. Also, if it isn't clear, we use p for the momenta for rainbow dash instead of k, because the different observers will have a difference. Well, they'll measure different values of momentum. So that's why we use k and p instead of just k for momentum. Now, since phi of tx is equal to phi of n epsilon, this is actually going to imply that this box over here is equal to this over here, and this is equal to this over here. The reason is that the Litecoin coordinates, right? Well, under the Litecoin coordinates, we have negative and positive frequency parts. And the Litecoin coordinates will not mix the negative parts with the positive parts, meaning that the expression that has negative k is going to be equal to the b negative k. And then the expression, the purple one that has positive k, so this and this right here, is going to be equal to this one and this one over here. We can't have this being equal to this because this has k and this has negative p. So we can't have those being equal to each other. Also, I should mention this is being integrated, right? So this is equal to this under the integral. So in other words, to be a bit more explicit, 0 to infinity of dk over 2 pi square root of 2k of a of minus k e to the ikx plus a conjugate minus k e to the minus ikx plus is going to be equal to this over here, and it's going to be analogous for the positive momentum. Now, I should mention this. X tilde plus is defined as n plus epsilon, and x tilde minus is defined as n minus epsilon. Again, we get an analogous expression for positive momenta, and that's going to be this right over here. So again, remember that our spirit of the video, like what we want to obtain, is b of p and b conjugate p in terms of a of k and a conjugate k. So how can we actually do that? Well, we actually have our ingredients right over here. So we know that this is going to be equal to this over here, right? So what we want to do now is we want to isolate b of p and b conjugate b. So how can we actually isolate them? Well, we can use the Fourier transform, because remember that phi of k equals the integral over dx over 2 pi e to the minus ikx phi of x. That's the Fourier transform, right? So that's going to isolate phi. It's kind of hard to explain, but let's just use the Fourier transform, and you guys will see. So what we do is take the Fourier transform, but we're going to use x minus here, x tilde minus e to the minus I p prime x tilde minus, and this is going to go from negative infinity to infinity, then 0 to infinity dp over 2 pi square root of 2p So here is the Fourier transformed value. And since we did that to the B expressions, we have to do the same thing to A. So what we can do now is explicitly evaluate what this is going to be. So let's take this over here. We're going to copy it, paste it right over here. So how do we actually Fourier transform this? Well, what we can do is exchange the order of the integrals. Is that a valid operation? We'd have to prove it, but let's leave the proof to the mathematicians. So this is going to be 0 to infinity. Now, something I want to mention here is why do we have this over here? Remember that in the Fourier transform, right? We had that phi of k equals the square root of dx e to the minus I kx phi x. This is that like factor, right? The Fourier factor. Or maybe this is called the Fourier factor. Whichever one's called the Fourier factor, I'm just gonna call this the Fourier factor or the plane wave. And this over here, we'd have to have that in order to properly Fourier transform this expression. So that's how we add that exponential there. And it's being multiplied by that. So we can just distribute this inside. And that's going to give us. So now what we can do is we can pretty much like simplify that part. That'll give us this. So we get this right over here. And this is where the Fourier transform can finally be done. All right. So all we have to do now here is we can actually explicitly integrate this over x. And the answer to this part over here is going to be, I hope that you guys can see this, it's going to be 1 over square root of 2p b of p delta of p minus p prime, and then plus b conjugate p delta of p plus p prime. And then the integral from 0 to infinity of dp over 2 pi of this whole thing. Okay, so how do we get this? Well, because the integral of this, like think about it this way, right? This term does not depend on x tilde. So we can just move that to the front. Or really we'd have to just show this inside. But like the terms that don't depend on x tilde, we don't have to like explicitly integrate those terms, right? And the integral of this with respect to x tilde is going to be delta of p minus p prime, right? Because of how the delta function works. So that's how we get this over here. So we can actually integrate this again, but over p, and that's going to give us 1 over the square, well, it gives us two answers actually. It's going to give us 1 over the square root of 2p b of p if p equals p prime, and then 1 over the square root of minus 2p b of minus p, or b of minus p prime, if p equals minus p prime. So I should really technically say, I should really call this p prime, right? I should really call this p prime as well. So if we take p prime to be positive, we're basically saying that if our momentum is positive, here is our answer. If our momentum is negative, then here is our answer. And actually, we should recall that we should have a 2 pi over here, by the way, because when we integrate over the exponential, we get factors of 2 pi. So those 2 pi's can be moved to the front, and then we'd have 2 pi divided by 2 pi, and that'll just cancel out. So there would be no 2 pi left over. No more pi's left over. So yeah, so this is our answer. It's pretty nice. So if p is positive, we have this. So let's take p to be positive. And if we take p to be positive, we can say that b of p equals the square root of 2 pi times, or square root of 2p, and since p equals p prime, we can still use p here. P equals the square root of 2p times this entire thing right over here, pretty much. All we're doing, because remember that we first had this over here, right? And we found that this was just equal to the square root of 2p, or it was equal to 1 over the square root of 2p, and then b of p. So to isolate b of p, we'd have to multiply both sides by the square root of 2p. So that's why we have that over here. And what we can do now is we can move this inside of here. I'll give us b of p equals the integral of this. Okay, so now we have this. So this over here. All we did was that we moved this into our integral. So that's going to give us square root of 2k over the square root of 2p. Now square root of 2k over the square root of 2p will just be 2k, or will just be the square root of 2k over 2p, or the square root of k over p. So that's going to leave us with, this is being integrated over this, to be clear. And now what we can do is we can just move the exponential. Again, we're just going to switch the order of the integrals. We're going to move this exponential on the inside. That's going to leave us with, so we now have this over here. And yes, this integral is really, really complicated. But this is going to be equal to, again, b of p. It may not look like it right off the bat, but we've actually done what we were trying to do. Recall that we were trying to write b of p in terms of this over here, in terms of a of k and a conjugate k. And it turns out, with the help of Twilight and Rainbow Dash, we actually did that. We have written out b of p, which is over here, in terms of a of k and a conjugate k. So we've done what we were trying to do. Now, to make this a bit more nicer to look at, let's try to, what can we do? We can define some function f of kp, where f of k is equal to this. And this means that we can write b of p as the integral from 0 to infinity dk square root of k over p times a of k f kp plus a conjugate k f minus kp. And we can paste our formula over here, and then we can immediately match up our coefficients, the Bogoliubov coefficients, and we'll see that a, or alpha kp, is just going to be equal to the square root of k over p, f kp, and then beta kp equals the square root of k over p, f minus kp. And since the exponential value of the number operator that Rainbow Dash is going to use is going to be equal to the integral of dp, or the integral over dp, and then dk of beta kp squared. This means that the outer particle, ignore all of this over here, you didn't see that, and that's going to be equal to k over p f of minus kp squared. So this is going to be the number of particles that Rainbow Dash sees. Okay, but this doesn't really look like a number, right? It looks like a bunch of letters. So we're not really finished, right? So we should first recall what f of kp is going to be equal to, or really f of minus kp. So here's f of minus kp. So it's this over here, right? Notice how we have an x minus and an x tilde minus. So we have two different variables. That's not good. So what we want to do here is write out x minus in terms of x tilde. So to do that, we have to first recall the definition of x tilde. X tilde is going to be epsilon plus. So x tilde is going to be epsilon plus or minus n. And then x plus or minus is going to be x plus or minus t. So we want to recall that t equals 1 over a e to the a epsilon. This and then this equals this. So this means that x plus t is going to be equal to 1 over a e to the a epsilon, and then this plus this. And it turns out that this is actually going to be equal to e to the a n, due to how the hyperbolic functions work. Sinh plus hyperbolic cosine is going to be e to the a whatever, so it's going to be e to whatever inside. So this means that x plus t equals 1 over a e to the a times epsilon plus n, and then analogously, x minus t is this. So this means that we can immediately write out x plus as being 1 over a e to the a x tilde plus. So yeah, and then that means that x minus equals this over here. So we can just write this out as this dx over 2 pi e to the minus I k, and then this is going to be pretty confusing to write out. So 1 over a e to the a x minus and then e to the minus I p x tilde minus. This is going to be equal to this. And then we're going to have, so this is going to be raised to that. So really it's going to be e to the, who cares? We care. It's going to be e to the minus I k over a times e to the a x tilde minus, because we can multiply them, and then times e to the minus I p x tilde minus. So that's just going to give us e to the minus I k over a e to the a x tilde minus I p x tilde minus. So we can actually do some rewriting, and we'll see that this is going to be equal to exponential. We're going to use exp instead of e to make this a little nicer to see. So minus I k over a e to the a x tilde minus, and then minus I p x tilde minus. So this is our answer for what f of minus kp is. So we want to calculate this integral. There is actually a way to sort of go around that. We can actually get our answer without solving the integral. So we can use the property where f of kp equals f of minus kp e to the p pi over a. That's some property, and I might be wondering, how do we actually show that this is true? Well, we have to use some complex analysis to show that this is true, which we'll be talking about in the next video. But for now, let's just take this, and using this property, we can actually do a couple of things. So first of all, we have to use another property where we know that b of k, b conjugate of k, not k, p, b conjugate equals 2 pi delta of k minus k prime, right? Let's take another look at our Bogoliubov transformation. It's this guy right over here. So we can actually just sub in the Bogoliubov coefficients. We can sub that in to our commutation relation. So this means that the commutator of this integral, dk alpha k p a k plus b k. Also, by the way, we're using an alpha here. I know it kind of looks like an A. I think in my last video I used like a different letter because alpha is kind of. I think I used gamma instead. But I guess because we're gonna like use alpha for today's video. So now we'd have this commutator or whatever the verb is with this over here. So now we're going to have a prime ak plus beta k p prime a conjugate k. And that's just going to be equal to this right over here. And we are using a k prime here. You guys are going to see why we're going to use it in just a moment. So we know that this is going to be 2 pi delta function of k minus k prime. And then all of this should be equal to delta of p minus p prime, since the commutator of b conjugate b prime equals delta of this. So, it should be 2 pi, actually, 2 pi of that. And then these pi's are going to cancel out, and that's going to, and then we can, of course, integrate over k prime. That's why we use the k prime here. We can integrate over k prime, let k equal k prime, and that leaves us with the integral. This should be from 0 to infinity, technically speaking, since the energy is positive. dk of alpha k p alpha conjugate k p prime minus b k p or beta k p prime, and that equals delta of p minus p prime. And technically speaking, we should have had like k primes over here next to the k, but since k equals k prime, it's not a big deal. So now what we can do is we can use our values for the Bogoliubov coefficients, which are these over here. And by plugging those guys in, we have 0 to infinity of dk of alpha kp. That's going to be k over p prime, right? Yes. Conjugated. And that should equal delta of p minus p prime. So now we can use a formula that we pulled from the sky. This one right over here. We are going to prove this formula in the next video. And yeah, we're going to use this formula to simplify things a tad bit. K over p of, now since f of kp equals this over here, f of kp is f of minus kp e to the p pi over a. So e to the p pi over a. And then f conjugate of minus k p prime e p prime pi over a. And then that's going to be minus f of minus kp f conjugate minus kp prime. So we did this so that we'd have like terms over here. And because of that, we can do some factoring. We can factor out the f of minus kp. That leaves us with e to the p plus p pi, or pi over a. This is a prime, by the way. Then pi over a minus 1. Oh, we should actually, technically speaking, have f minus kp f conjugate minus kp prime. And then times this. All we're just doing is factoring that out. And that equals delta of p minus p prime. So what we can do now is we can do some division. Since this term does not depend at all on k, we can just divide that out, actually. So after factoring the f function, you can divide. And that means, that implies that the integral from 0 to infinity of dk, k over p, f of minus kp we're going to say that squared equals delta of p minus p prime over e to the p plus p prime pi over a minus 1. So let's erase this. And now what we can do is we run into a bit of a problem. So if p equals p prime, that means that we now have that the integral from 0 to infinity of dk k minus 1. Now, this is actually exactly the integral that we were trying to find right over somewhere. This is a lot of math, actually. Right over here. Again, we were trying to find this. Let's actually copy this. We're trying to find what's in the yellow over here. And that's exactly what's here, right? So we've calculated what this integral was, and it's this right over here. But we have a divergence. This is going to be infinity, which means that rainbow dash sees an infinite amount of particles. So she'll see an infinite temperature, which makes no sense, right? So the solution is to say that we are working with a finite spatial volume, which will mean that this would just become some finite constant v if we work in a finite volume. And then we could take the volume to be equal to 1 if we want to. So that solves the problem somewhat. And that means that we now have that the total number of particles that rainbow dash is going to see will be the integral of d over dp, integral, dp, and then times 1 over e to the 2p pi over a minus 1 from 0 to infinity. So now we have this over here. We run into another problem. This also diverges if you let the momenta run arbitrarily high. And that's because that 1 over e to the x minus 1 behaves something like, if I recall from memory, like a natural log of, I think, x minus 1 and then plus x or minus x plus c. Something like that. Don't quote me on it. Something like that. And this is going to diverge, right, for an infinitely large x. So this means that we still have a divergence here. But if we sort of ignore the integral over the momenta and focus just on this yellow part over here, you'll notice something that's really important. This actually looks a lot like the Einstein distribution function. And this from thermodynamics tells us the probability that a particle will have some energy E. This formula comes from statistical mechanics, where this T over here is the temperature. I made a video on the black body radiation. It's the first video in my quantum mechanics series, so I recommend checking that out. But the basic idea here is that this formula describes black body radiation, where T is the black body temperature. And again, N of E is a probability that some particle will have some energy, or the black body will have some energy, really. So this means that, that looks a lot like this right over here. In fact, let me just copy that. Just copy this formula and paste it. So it looks a lot like that. In fact, if we sort of say that maybe they're equal, right? So if we take our hunch, or really Unruh's hunch, 2p pi over a minus 1, if we were to assume that they're equal to each other, e over t minus 1, this means that 2p pi over a, let's erase this redundant stuff, equals e over t. And since e equals p for massless particles, this means that we can rearrange some things. We would find that t over e equals a over 2p pi. We multiply both sides by e. This will cross cancel out. And we have t equals a over 2 pi. And that is the temperature that rainbow dash is going to see. So yeah, if we were to just ignore the divergence here, focus on this term, we will still have some problems here. We can solve this issue by saying that there's a momentum cutoff, like a highest possible momentum. So we could do that, but if we were to sort of ignore this integral and focus on this distribution here, it implies that the temperature of the vacuum that rainbow dash will see is equal to a over 2 pi, where a is the proper acceleration. So if we could go all the way back up here, this means that rainbow dash, right, since she's accelerating, she's going to see particles present. And the particles, right, this radiation is going to look like black body radiation. And the temperature that forms as a result of the particles moving around with kinetic energy is going to be proportional to her acceleration. Now, twilight sparkle is going to see 0 particles, right? And this looks like a problem, because what if Rainbow Dash is carrying some potion, some magical friendship magic potion, or maybe one of Flim and Flam's tonics? Well, then what if the particles that Rainbow Dash sees makes the potion like catch on fire, right? Because if it's like hot enough, if the temperature is hot enough, it's going to catch on fire, right? So how will Twilight explain the fire that she sees from the potion if she sees no particles? Well, it turns out that Twilight will see Rainbow Dash's quantum field, or she's going to see the potion being coupled to the quantum field. And since Rainbow Dash is accelerating, that's going to cause some sort of friction with that quantum field. And that friction will generate temperature. That's a very simplified way of saying it. We can actually make this a bit more precise by directly coupling the potion with the field, which we will be doing in the future video. And so basically, I know I'm not making much sense right now, but Twilight Sparkle can actually explain the temperature. So she will actually see a temperature as well, but she won't explain it as being caused by particles. She will instead explain it as being caused by the acceleration of Rainbow Dash. And we can do a precise calculation, which we'll be doing in a future video. So that's pretty much it for today's video. That is going to be the temperature that Rainbow Dash is going to see in the vacuum. And we also calculate the number of particles that she sees as well, which was equal to the integral over dp times that 1 over e to the 2 pi, whatever it was, minus 1. So yeah, with that being said, that's pretty much it. Thanks for watching. So yes, you can outpace light, but you can't outpace the radiation that the horizon generates. Thanks for watching and have a great day. Bye.